Welcome back to our channel where we explore the mysteries of the quantum world. Today, we'll be discussing one of the most important topics in quantum computing, quantum error correction. As you may know, quantum computers use qubits instead of classical bits to process information. However, qubits are extremely fragile and can easily be disturbed by environmental noise. This is where quantum error correction comes in. Quantum error correction is the process of detecting and correcting errors that occur during quantum computation. It's a crucial part of quantum computing since it helps to maintain the integrity of the data being processed. There are different types of quantum error correction codes, but most of them are based on the principles of encoding information redundantly across multiple qubits. This redundancy helps to detect and correct errors in the quantum information. The most common type of quantum error correction code is the 3-qubit code. This code uses 3 qubits to encode 1 qubit of information. The 3-qubit code can detect and correct any one error that occurs in the 3 qubits. However, as the number of qubits in a quantum computer increases, so does the complexity of the error correction codes. This is where the concept of fault-tolerant quantum computation comes in. Fault-tolerant quantum computation is the ability of a quantum computer to continue to function even when some of its qubits are in error. It requires the use of more advanced error correction codes and fault-tolerant quantum circuits. Despite the challenges, progress has been made in the field of quantum error correction, and researchers are continuing to develop new techniques and codes to improve the performance of quantum computers. Quantum error correction is a set of techniques used in quantum computing to protect quantum information from errors caused by environmental noise and other external factors. In classical computing, error correction is done by duplicating data and comparing the copies to detect and correct errors. However, this approach is not feasible in quantum computing, as copying a quantum state is not possible due to the no-cloning theorem. Instead, quantum error correction relies on a technique called quantum error correction codes. These codes encode the quantum information in such a way that errors can be detected and corrected without needing to copy the state. The most common quantum error correction code is the surface code, which is based on a two-dimensional lattice of qubits. In the surface code, qubits are arranged in a grid pattern, with each qubit being connected to its 4 nearest neighbors. The code is designed so that errors can be detected by measuring a set of qubits known as stabilizer qubits. If an error occurs, the stabilizer measurement will give a different result than expected, indicating that an error has occurred. By using multiple rounds of measurements, the code can detect and correct errors. Quantum error correction is a critical component of quantum computing, as it enables quantum computers to perform complex calculations without being derailed by errors. As quantum computers continue to advance and become more powerful, quantum error correction will become even more important for ensuring the reliability of these machines. With this in mind, it is important for researchers and developers in the field of quantum computing to continue to work on developing and refining quantum error correction techniques. This will help to unlock the full potential of quantum computing and enable it to be used for a wide range of applications, from cryptography to drug discovery to materials science. Error correction can be resource-intensive. Correcting quantum errors requires additional qubits and gates, which can be computationally expensive. Therefore, quantum error correction protocols often involve a trade-off between the level of error correction achieved and the resources required to achieve it. Different types of errors require different strategies. There are various types of quantum errors, including bit flip errors, phase flip errors, and more complex errors that affect multiple qubits at once. Different quantum error correction protocols are designed to address different types of errors. Research in this area is ongoing. Quantum error correction is a rapidly developing area of quantum computing research. Scientists and engineers are constantly developing new protocols and techniques to improve the level of error correction that can be achieved. Quantum error correction is important for scaling up quantum computers. As quantum computers continue to increase in size and complexity, the need for effective error correction becomes increasingly important. Without error correction, quantum computations would quickly become overwhelmed by errors, rendering the results useless. Quantum error correction is an active area of collaboration. researchers from across academia and industry are working together to develop new error correction protocols and techniques. This collaboration is crucial for advancing the field and making progress towards practical, error-corrected quantum computers. Quantum error correction is an essential tool for maintaining the accuracy of quantum computers. Quantum computers are inherently more error-prone than classical computers because of the fragility of quantum states, which can easily be disturbed by the environment. Error correction is therefore crucial for ensuring that quantum computations are accurate and reliable. There are several types of quantum error correction codes, including the 3-qubit bit flip code, the 5-qubit code, and the 7-qubit Steen code. These codes are designed to correct different types of errors that can occur in quantum systems, such as bit flip errors and phase flip errors. The basic idea behind quantum error correction is to encode quantum information in a redundant way so that errors can be detected and corrected without destroying the original information. This is done by creating a larger, more complex quantum state that includes the original information and additional qubits that serve as check bits. By measuring the check bits, it is possible to detect and correct errors in the original quantum state. The process of quantum error correction involves several steps, including encoding the information, detecting errors, and correcting errors. This process can be quite complex, and requires careful design and implementation in order to be effective. Despite the challenges involved in quantum error correction, progress is being made in developing more advanced codes and techniques for detecting and correcting errors in quantum systems. As quantum computers continue to evolve, error correction will become increasingly important for enabling practical and reliable quantum computing applications. In summary, quantum error correction is a vital component of quantum computing that enables accurate and reliable quantum computations. It involves encoding quantum information in a redundant way and detecting and correcting errors to maintain the accuracy of quantum computations. Ongoing research is focused on developing more advanced codes and techniques for effective quantum error correction. That's all for today's video on quantum error correction. If you have any questions or comments, feel free to leave them in the comments section below. Don't forget to like and subscribe to our channel for more videos on quantum computing.